Hello, this is Lab 3 Circuits by Aaron Christian. The purpose of this lab was to predict the behavior of a circuit with parallel resistors, to measure the potential and observe the behavior of resistors and capacitors. The system for this lab is the circuit, and the surroundings include everything else. Important physics concepts for this lab are Ohm's law, which is the voltage is equal to the current times the resistance, the node rule, which current is preserved in and out of a node, and the loop rule, which is the sum of all potential differences around a loop are zero due to conservation of energy. So for this lab, we took two 1.5 volt batteries, two resistors, and two ammeters set up in the configuration shown in the diagram. We predicted the currents of I1 and I2 that would be measured by the two ammeters. So the resistance total is equal to the resistance 1 plus resistance 2, which we found to be 147 ohms. And then we found the current to be 0.02 amps. So on this slide we have our real world experimentation. So on the left we have two ammeters set up, and as you can see they both say 2, so 2 amps are flowing through the wires, and nothing changed when it went through the resistors. But on the right we turned one of the ammeters into a voltmeter, and that voltmeter read 3 volts while the ammeter read 0 amps because the voltmeter has a very high resistance, which drops the current to nearly 0. So on this slide we have the configuration, and we were told to measure the volts at the different points, and all these voltages equaled up to 0. When reading with the voltmeter, the ammeter didn't change since the voltmeter had a very high resistance and is in parallel, so not much charge was actually flowing through it. Below we have a graph showing, so as it pushes through the batteries, the volts rise up, and then it slowly decreases as it goes through the higher resistances. So on this slide we have the diagram from the previous slide, and then we found that the resistance of the 47 ohm resistor was 47 ohms, and the resistance from the 100 ohm resistor is 100 ohms, while the wire and the amp meter had essentially 0 ohm resistance. So the next part of our experiment was to create an RC circuit. We made this RC circuit using a 20 ohm light bulb, a 9 volt battery, and a 200 mF capacitor. When the circuit is connected, the light bulb starts out very bright and then dims while the capacitor builds charge. When we disconnect the battery and complete the circuit through the capacitor, the light bulb starts out bright and then starts to dim again, but as the capacitor loses charge over time. So we continue to experiment with RC circuits. So for this circuit, we used a 9 volt battery, a 30 ohm light bulb, and a 200 mF capacitor in a series. We predicted the RC value to be 6, and then through our experimentation, it turned out to be 6.9. And we used that to RC was equal to -1 divided by the slope of the natural log of V voltage over voltage at time 0 versus time. And the slope is the slope of that natural log, which is y equals -0.145x minus 0.0208. Some errors we could have gotten is just improper timing with the stopwatch. So for our what if and why question, if you were to charge a capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? So theoretically, the capacitor would charge nearly instantaneously, but due to resistance and like minor resistance in amp meters and wires, it would not be able to charge instantaneously.